So for this talk, I wanted to see, kind of try to aggregate the lessons learned. Because I think like a lot of us, when we start doing these deep models, they're really exciting. We run the examples and they work, and then we try it on our own data, and we start getting nans, like in the loss, and you're just, wow, like you don't know how to react to it. And so a lot of this just comes from experience, just hitting your head hard enough against the wall enough times that you break through that wall, and then you do it again and again. Um, so my background, a lot of you guys already know, because I know a lot of you guys. So my career has kind of been all over the place. So I studied chemical engineering, and actually that's the case for all the data scientists at Higher View. We did not study a formal data science track because we went to school and they didn't have such a thing. So I did chemical engineering. We have astrophysicists um, that in Lindsay, what type of physics are you? You're not astrophysics. Or you're closer to me, closer to like material science, right? Okay. Yeah. So I did that for undergrad. I did my master's in that. This is actually some of the stuff I was doing for my research, gold nanoparticle arrays. And so I did some of the image processing for that. Then I went and worked for IM Flash for 5 years, and that's an Intel Micron joint venture. So if you have an Intel SSD, and even in the iPhones, a lot of that NAND flash actually comes from this plant here in Lehigh. They're kind of the alpha fab. So when they do the R&D up in Boise, it comes down here, and this fab actually scales it, and they lead the other fabs in yield and R&D and stuff. Later. And then I went and worked for a hedge fund. So I think that was probably one of the most important points in my career as far as like converting over to data science. So I did that. We had $1 million GPU cluster. We would do 10 million back tests per day. So we were using CUDA, weren't using any deep learning, just all heavily optimized matrix math on the GPU to do these classical stock portfolio balancing and different types of models. So the hedge fund was always long and short. So they're perfectly balanced. So it didn't really matter what the market did as long as their bets were, more or less averaging to be correct based on their the S&P 500 stock or 1500 stocks they're trading. And then a little 3.5 years ago, I joined Higher View, and and I've got a whole slide for Higher View after this. So I think one of the things that I appreciate more now in my career is it doesn't really matter what you do for work; it matters what you do during your time off. Like you want a job that you love, but before with some of the other jobs I've had, I felt like I lived to work, and at Higher View, I definitely felt like I work to live. And so this is me this season. I go backcountry skiing as much as I possibly can in the morning. I'll be going Friday because we're kind of running out of snow. So that's a real passion for mine. So Higher View, if you guys don't know what Higher View does, so Higher View does digital interviewing, and so everyone in the room has interviewed, right? Like we've all had jobs before, and we have future jobs that we're going to have to interview for. And the current hiring process is still actually really bad. Like you pick your favorite company, Google, there's local companies too. You hear about kind of the screening process, how people come into the company, and they do a lot of things wrong. So some of the common things that people do wrong is they do an unstructured interview. So the interview I give you today would be different if you came in tomorrow, and this individual got a different interview than that individual, and that's not very good. They've seen you get higher accuracies if you have a consistent interview with fixed questions. And you do even better if you have a psychologist that actually figures out what those questions should be based on top performers. And so right now the hiring process is you'd go to an applicant tracking system like Adobe or these other companies that have them. You'd submit, and then your resume kind of goes into a black hole. You may not get called back. I applied to Adobe once. I can't remember how long ago. I was never contacted. Like no rejection, just into this abyss. And we heard, and so it's one of those things where there's a big luck component. If you come in late in the hiring cycle, it doesn't matter how good you are, you're going to get a rejection, and really no human ever reviewed you. So with Higher View, we kind of skip that entire process, resume, phone screen, interview. We can actually go directly to the interview. So you get a chance to show off not only your technical skills that you might have on your resume and LinkedIn, but also your communication skills and your technical skills in an interview. And then the stuff that the data science team has been working on is we use machine learning to predict the interview outcome. So if you really are a good candidate, the likelihood of a human seeing your interview it's much higher than it would be without the machine learning. So if there's thousands of candidates and you are good compared to what's been learned from historical behavior, then you've got a shot. And the thing I get excited about is this now matters. I think the value in where you went to school, did you go to Ivy League, community college, that stuff will become less important, and it will truly depend on what really matters. So it kind of opens the door. And actually, Higher View has some awesome press. Goldman Sachs, I think it's Goldman Sachs, or is it one of those banks? They canceled their on-campus recruiting. So before they had an Ivy League bias. They go and recruit at Harvard and these different Ivy League schools, but they canceled it. And so that's an example of higher view kind of broadening the gate for some of these companies. And then we also have examples with machine learning that we're quite competitive with some of the assessment tools. So they already have some stuff right now where you can take 100 questions and they'll decide, are you a good fit for Goldman Sachs? And if you guys have ever done that, it's a real pain. Like no one wants to sit down for an hour. Um, I did an assessment this year for one of our customers. It was an hour and a half. And they told us before, like, oh no, this is only a 30-minute assessment. And like an hour and a half into it, you're trying to decide, like, I can't remember what the questions were. Like, if you were an ice skater, would you spin or jump? Like, they're just like I don't know, like, I'd crash. Like, they're just kind of silly questions, but there's some, you answer enough of those, and I guess there's some statistical validity. They're not garbage, but I think compared to this new machine learning, we definitely have an advantage, and we have a lot of work to do to improve it even more. So I'm also involved with a startup right now called Ziff, and what we're attempting to do is we're doing machine learning as a service. So we're like a lot of other machine learning as a service companies out there, except our focus is to be the simplest point of entry. So we don't want you to read pages and pages of documentation like you have to with Google and Amazon and Microsoft to even use their products. We're looking at doing a very simple REST API. So this is an example of a deep learning call where someone's sending a URL to predict based on a pre-trained deep net. And so the stuff we're talking about today, we've automated that into kind of best practices on the cloud. So if you want to build predictive models on text, images, you don't really have to think about, well, what deep net do I use and how do I label, like how do I do my training and validation set? You just take those images and you point your S3 bucket to our API, or you literally send a tar file or a zip file with folders, and we do the deep learning, and then we give you an API that you can hit. So that's what we're working on. So I think now we're going to switch gears and go into deep learning. So I think this is resonating well with people that I talk to. So deep learning is really significant because it's kind of it's a significant step in human evolution for what humans can do. And so before the year 2014, we were kind of capped at what we could do on different types of image classification problems. So I'm going to walk you through what we're looking at. So MNIST is kind of your hello world default example. It's 10 handwritten digits, so 0 through 9, and you need to predict. I'm going to give you an image of a handwritten digit, like a 4, and you have to predict, is this a 4 or is it a 5? And this classical set has 60,000 images that you can train on, and then there's a validation set of 10,000 that you can predict on. And you can actually use a Bayesian method. So I'm showing you accuracies on my validation set. You can use a naive Bayes method to predict the image based on the pixel data. And you can get 83.5%, which is actually quite good, because random would be 10%. So 83%, that's great. You can see if I use a linear logistic regression, I'm getting 91.9. If I use XGBoost, which is still the most popular Kaggle structured ensemble method out there. So some people that win at Kaggle, they'll take XGBoost when they do some very aggressive hyperparam tuning. And then maybe the most aggressive way you could do machine learning with with classical methods would be a grid search, and that's what DataRobot does. So if you know DataRobot, they do a very aggressive grid search where they're testing XGBoost, logistic regression, Bayesian method, and they test all these. They do hyperparam tuning, and then at the end they'll even do a small ensemble of those, and that's their product. So the best you can do with classical methods, you're getting like a 94.78. And with deep learning, I think with the dumbest model I could possibly come up with deep learning, I'm getting like 97. And this kind of shows you the evolution that you start with very simple linear models, you transition to decision trees, XGBoost, which is a kind of a chain of decision trees, and then you get into these deep nets. And the thing that's significant is, the thing that really hits home for me is the model size. So if I start here with a linear regression, I can actually send you a text message. Like if you said, hey, what's our linear regression for our hiring model? GPA, Ivy League, race. I'm just kidding. Or like you might have like 3 things that you're going to predict on. And you're like, what are our coefficients? I could send you a text message. I'd send you 3 slopes and an intercept, and you could go type that in and do something. So it's very, very small. As you start going up in these models, you go into the kilobyte range, where I'm not going to text you a decision tree, and I'm definitely not going to text you an XGBoost, because some of these can be like 300 decision trees. I might email it to you. But when you get into the deep nets, you suddenly get into hundreds of megabytes, where the largest ones can be a gig when they're uncompressed in memory. So think about that. We're going from kilobyte models to gigabyte. And I think a few years ago, people would, like even 10 years ago, people would have really resisted this. But we still see this resistance now where people are absolutely convinced that there's no way these deep nets can generalize and that they're prone to overfitting, but actually they generalize really well. And they're the state of the art. And then I have the singularity in there. It's supposed to happen around the year 2045. That's when machine learning actually outpaces the human's ability to comprehend what it's discovering. So it's kind of like this runaway reaction. So, be patient. So the other way I like to introduce deep learning is I like to tell people that they already know what it is. So if I'm talking to a manager or someone who's less technical and they're trying to understand what deep learning is, I'll say, well, it's just another tool in the tool shed for analysts, but it's a really fancy one. It's like a brand new power drill that can do everything. And you know what deep learning is because your brain does it. It does a form of it every day. So if I'm looking at a fork or a unicorn cloud in the morning, and I'm like, oh, that looks like a unicorn. Why is my brain deciding that's a unicorn? Well, the horn is important, the feet are important, the face is important. And so what I did with my mind is I built a basic feature ensemble. So some of the features are tiny, some of them are big. The other example I'll use is if I'm looking at a fork, why do I know that's a fork? Well, I used micro and macro features, and I used that whole soup of features together to make a decision. But for humans to compete against deep learning, our feature ensembles are actually almost embarrassing compared to what the computer does. So if it takes you it's hard to quantify, but if I had to guess, I'd say it definitely takes me fewer than 20 features to decide that's a unicorn. But the computer will use tens of millions of coefficients to decide that's a unicorn. So my 20 versus the computer's 20 million. And there's lots of examples now where the computers are beating humans head to head. And higher view, we actually have a gender classification model that is so there's lots of examples where we are beating humans, but when we started doing gender classification from image here, I didn't can we really beat a human? If I show you, if I show you 100,000 humans, men and women, you'll probably get them all right. So how am I going to beat you? And what we noticed is there's actually the humans, they self-classify, and there's an error rate. So 8 out of 10,000 humans who check the box that say they're male or female will actually make a mistake. And this is not transgender or something. It's actually, they just made a mistake. And what really matters is what the recruiter thinks. So the recruiter will think these 8 people misclassified, and the deep net is better. So the deep net only makes like 2 mistakes in 10,000. So that's superhuman accuracy when it comes to data gathering, which I think is pretty exciting. So this is the dumbest deep net that I could possibly come up with for this unicorn. So if I have a unicorn, I have 3 convolutional filters. You can think of those as just individual features that are being discovered. And they're represented as a 3x3 matrix for each one. I do a max pooling, which is downsizing to macro features, and then I have flat layers at the end. And for this model, I want to predict, is this image a unicorn, a panda, or a baby? So this is a baby deep net. It's very simple. And literally, if I solve this for MNIST, this is what I get. So these top 3 are convolutions. They actually represent numbers based on the shading. And then the bottom layers, it's kind of messy and hard to see. Those are the coefficients that I solve for. So this deep net, which is about as dumb as you could get, very simple, three layers, 2 flat layers, I'm getting 97.45. That's much better than anything that anyone had done with classical methods. So if we took the smartest person in the room and they spent a day or a couple days using classical methods to really crank on this problem, they probably would not be able to do better than that. So that just kind of shows you the power of deep nets with the spatial aggregations they can come up with. And this shows you how simple the code was in Keras. So this is Python-based, it's Keras, it's my favorite library. It's very, very simple. I hate Caffe, because Caffe you have these text files that represent the model. And for your larger text files, you'll have a 3,000 line text file representing the model. Keras allows you to do some really cool stuff where you can dynamically change the model. I can lock different layers on the fly. I can actually I could replace sections of the model because it's a piece of code. I can play with it. And just just a quick tangent. So I like to kind of spam stuff on LinkedIn to kind of see what agitates people and what people react to. So the most engagement I've ever had within a couple-day period was, I think, when I published Ashley Madison affair data. I got 13,000 engagement, reactions to that set being published. And I posted on LinkedIn and I said, I hate TensorFlow and I hate Caffe. Use Keras, and it got 40,000 engagements. Where it was the most I've ever had, just because I said TensorFlow is the most popular machine learning library right now, and I really don't like it. I guess some other people feel that way too. So I love Keras because it's just so simple. This is this is what a bigger model might look like. I actually have 32 filters, and then I have a second layer of 32 filters. This is more like your hello world example. So if you're just starting into deep learning, I'd expect you to do something like this relatively quickly. You just kind of change a few lines of code. You're getting 98.99% accuracy. And our code really didn't change that much. We just added a few more lines. It's super easy to extend your deep nets and make them deeper and add more layers. So now if we want to improve the deep nets that much more, one of the issues we deal with if you have small training sets, I'd say small training set would be anything like under 500,000. So we actually have some data sets we played with that are much larger. I used to think ImageNet was big, so ImageNet is like 1.2 million images. But we have data sets that we've trained that are 6 million, 8 million, 9 million images, and you're training on 9 million images. And when you get data sets that big, this really doesn't matter as much. You can still do it, but it becomes less important. You're just fighting to get through these epochs when you have 9 million images. But if you have a small data set, this is really key. So data augmentation, you actually modify the image on the fly, so the deep net never sees the same image twice. And so stuff already built into Keras, shear, rotation, crop, and zoom. They have a data generator that you can call, and they already have all these defaults, so you can just change them to do whatever you want. You can do horizontal flipping. That does not make sense for letters and numbers, but it makes perfect sense for a face. So if you're doing gender classification, you can do horizontal flipping all you want. You would not do vertical flipping. If you're doing like something that does a lot like the whale competition on Kaggle, where you want to look at a whale in the ocean, then by all means don't do the flipping, but you can actually do 360 rotation. Because it doesn't matter which angle you're seeing the whale, you don't know in the future which angle you're going to see the whale from. So the net needs to generalize on all of those. So this can do all of that. And for this example, this shows our net getting bigger. So the first net had 23,000 unknowns. It's growing to 703,000. Now we have 28 million unknowns, and we're going to solve for those. So as we go up, these nets become harder to solve, but you actually get, if you can solve them and get them to converge, typically you get higher accuracies. And this is following a very classical net architecture that I'll talk about in a minute. Like, I think 28 million unknowns is hilarious. Like, I think about being in school 8 years ago and telling your advisor you're going to fit a model, you have 60,000 observations, but don't worry, you have 28 million unknowns. You're going to fit this model. Like, can you imagine, like, no, you idiot. That'll be ill-conditioned. Like, they throw all this stuff out. You can't solve that, but actually you can. You can solve it well. So these are some black magic tricks if you're fighting for more accuracy. So averaging isn't black magic. That's kind of common sense. So for people that hit these new records for ImageNet, like every 6 months or every year, the humans have moved the needle on ImageNet. So it went from like 14%, where now we're down in the 3%. I don't think we've gone under 3% yet, but we can classify 1,000 different classes, top 5 rank with a 3% accuracy, and I think our top 1 rank, where you actually predict B class, is like 80%, which for 1,000 classes, that's amazing. And so if you build the model 2 times, 5 times, 10 times, and you average those results, these models are stochastic, so they're random. They'll be different, slightly different every time. You'll actually do a little bit better. So we can build n models. I think in this example, I build 10. I build 10 different models. I can average their predictions. The other thing you can average is, it doesn't make sense for these, but for bigger images where they're not perfectly square, they do cropping. So I don't need to average the model. I can average the model, but I can also do like 10 crops. So a lot of times if you read the ImageNet white papers, they'll talk about cropping. So they'll say like 10 crop, 150 crops. So they're randomly cropping that image, and then they aggregate the scores coming out of the deep net. So something that people have mentioned, and I've seen this work in our case, is if you are doing augmentation, if you think about it, if you're doing like a shear and a zoom, and you can get some pretty wacky results. Like think about pictures of cats. So if I take pictures of cats and I'm shearing them, it's going to look a little off. Like you can still tell it's a cat, but it's not going to be like the cat you see on the validation set. So you still want to do data augmentation, but once you've kind of converged that net, you'll turn off data augmentation and you do fine tuning, where you knock your learning rate down a couple orders of magnitude, and you'll do 10 more epochs, or however many more epochs you want to, with no augmentation, and this will do better. And this is actually proof. So you can see for 18 different models, I went from blue to green. This is on MNIST. So my accuracy went up when I did fine tuning with no augmentation. And you can see it didn't go up a lot, but you're kind of, at this point, you're already getting 99.7% accuracy. So you're kind of like fighting for, you're kind of at the end of that diminishing return curve, where you're fighting for tiny little gains. But you can keep going. So layer replacement, this is a fun one I was playing with this year. So you can, right now when you solve deep nets, we kind of defaults to whatever the deep net would do. And if you think about it, the final layer is kind of like a logistic regression where you might decide you'd rather do something different. And there's nothing stopping you from doing something different. So in Keras, you can modify that final layer after you trained, and you can do whatever custom model you want. For me, I've noticed that ridge regressions work particularly, like they work really well. But you can even do like a random forest. So you can have a net hybrid that is literally gradient based regression or random forest. But for me, I've tested lots of different models, and a ridge regression will usually get you a slight boost. And actually, this boost is more significant than, like, look at the big gaps. You see these valleys where there was a huge gap in the improvement. So the ridge regression, it did hurt us on one model. We had no improvement on one model, but across the board with the ridge regression on the final layer helped. So this is after training. So you've already trained the nets converged, and you just swap out the final layer, and you train a ridge classifier, and that takes you up that much higher. So for this, when I sum all those together, I get 99.78, which is a 0.22% error. The record could be higher than this, but the highest record I saw posted on GitHub was 21%. So like, and actually, honestly, no one really cares about MNIST. Everyone cares about ImageNet. So I'm sure there's lots of people out there that could do even better than 21 if they cared to. So these are lessons learned. So I have 8 slides that I've put together on lessons, just key points if you're training deep nets, what you can do to have a competitive approach. So cutting edge cuts the most. So kind of common sense, if you are using deep nets, you need to make sure that you are up on state of the art. And you might think the state of the art would be something like a ResNet, but there's actually a lot of nets that have kind of come into the game since the ResNet that are more competitive. And so this shows you top 1 accuracy on ImageNet. So AlexNet was kind of the first one. You have the GoogleNet, you have these VGG nets, you have the ResNet, where this one, Inception version 3, they're showing that that is the most competitive. So if you're fighting for accuracy and all you care about is accuracy, well, Inception version 3 would probably be a good starting point. And they even have other nets beyond this that people have published. And I guess to tease you guys, the net that Ziff uses is not obviously most. And then on the right, if you care about timing, so one of our customers is a drone company where they want a deep net to run at 30 frames per second. And if you want a deep net to run at 30 frames per second, you're definitely not using some of these bigger nets. And so the thing you care about is how many parameters do you have, what's your accuracy efficiency per parameter. Because these VGG nets are really fat, they're bloated, they're not very efficient. A lot of people are starting to abandon them because these other nets actually have better efficiency. So you can see on this plot on the right, VGG 19 has the absolute worst accuracy per param. So it's the biggest bloated net with the least amount of benefit, where the GoogleNet is incredibly efficient. But you don't need to use GoogleNet. You could pick, and actually there's one called the SqueezeNet, which is like 50 times smaller. And that one should have been up here, but it's not on that plot. So you kind of have a trade-off. Is your application accuracy or is it speed? And you need to decide which side you're going to land on. So we talked about transfer learning at the last meetup. So we always start from a net that's been trained on a previous data set. We never start from scratch. And what we do when we start training is I think I talked about this on the next slide, is we do layer locking. So really, if you think about the net, you have the image coming in the top. It's not very interesting at the top, but down at the bottom it becomes very complex with features. So we unlock the layers at the bottom and we start training on those. And then as the net trains, we start unlocking and move our way up. And you really don't have to do that. You could just train the bottom 20% of your net and never change the stuff above it, and you would do really well. But to start these bigger nets from scratch, like Inception version 3, I think that'd be a fool's errand. Like, that'd be kind of dumb. You wouldn't want to start something like that from scratch. You'd always want to have it initialized on good convolutions coming from ImageNet, OpenImage, or there's other training sets out there. Learning rates. So a couple things that we've done on learning rates. So you want to decay the learning rate typically. Some people will do a step decay. They start with a high learning rate, like a 0.01 or 0.02, and then they start stepping their way down. Or you can do like an exponential decay. Layer locking, which I talked about. And then augmentation stopping, which we already talked about. You just stop all augmentation. Another lesson that we've learned is I'm kind of disappointed that Keras doesn't push. Keras kind of handicaps you out of the gate with in-memory data sets, like MNIST, and all these different examples. They can all live in memory with a whole training set, where in reality, when you're actually doing problems in production data, it can usually never all fit in memory. The nice thing that is in Keras that isn't really documented that well is this generator. So you can actually make a custom generator, and then you can call it a model fit generator. You can call, so with some of the stuff we've done with Ziff, we have custom generators that are making, they're pulling out multiple labels for a single image. But your generator could go pull data from S3, it could go hit a database, it can pull from a flat file, it could do whatever you want it to do. It could go pull from the internet. So if you want your generator to actually go download images from the internet or go do screenshots, your generator can do whatever you want it to do, and that will fit right into Keras, and Keras will just call that. So the output of the generator comes from this yield, where you're going to yield a batch of features and a batch of labels. So you can have multiple labels. So it's actually a really slick thing. So for all of our training, we use generators. We don't do stuff in memory. And then we use NVIDIA Docker. So NVIDIA Docker really helps. If any of you have stood up CUDA DNN, you've installed this entire stack, it's a real pain in the butt. Especially when you start installing like Torch and all these different dependencies. If you screw something up, you don't want to start over. So NVIDIA Docker and NVIDIA Docker Compose makes things really nice. You can check it in Git, you can have version control, you can collaborate with your team better. So we use NVIDIA Docker and NVIDIA Docker Compose. The other thing that we've noticed is we do much better if we do scaling when we're training. A lot of times when you're training a classifier, you have severe model imbalance. So in the case of HireVue, if we're doing top performers, only like 10% of our people are top performers. So you're dominated by the other class. And there's lots of examples in industry where you don't have good class balance. So we've noticed we do much better if we do stratified sampling for our batches. There's ways to address this with weighting and things, but we've struggled with that, and the stratified batching seems to really help. And one of the things you can do is you can actually just do more augmentation on your minority class. So if you have a small minority class, you can just do more augmentation on it to kind of drum that up. And then for continuous variables, we've noticed improvements if we do percentile scaling. It's kind of the same issue. If you have a tight bell curve and you're trying to do a regression for a deep net, you're dominated by the center of the bell curve where the errors aren't quite large, and you're not really penalized for the outliers like you should be. So we have a beauty model that we trained. It predicts age, beauty, and gender. And if you predict that if some dude, you say they're like a 5.6 versus a 5.9, that's actually a huge difference. It's a massive difference. And so to give the net the full penalty, we do percentile scaling. Does that make sense? So it depends on if it's discrete or if it's continuous. You can scale to get better improvement. And then the other thing that I think has been very beneficial is you really want, these nets can do whatever you want, and I feel like when I'm using Keras, that's the case. If I use TensorFlow or some of these other things like Caffe, I don't feel like I'm the master of the net. I can't just make stuff up. But Keras, you really are the master of the net. And so one training set, I can have the output be classification, so male, female. I could also have it be age, which would be regression, where it's a continuous number. I could have it be three things, where it's a hybrid. So we actually have a net that predicts beauty, age, and gender, where two of those are regressors and one is a classifier. Or the other thing you can do, which is you can actually have the output be an image. So the only thing that's changing is the bottom of my net. The training set did not change. The bottom of the net is changing to modify it to be whatever you want it to be. And these really cool examples on the end, you can actually have an image colorization. There's lots of examples of that where you have a question? So it's just one output, and then you change your loss function. So your loss function is not categorical, cross-integrity, it's going to be just MSE or some variant of that. And yeah, so so the node spitting at the end, it's just going to spit out a continuous number like age. So the one node coming out the bottom of my net would be a number from 10 to 90 or whatever. And then I'm scoring that based on my mean squared error when the net solves. So it's actually pretty simple to do regression net. And then for the matrix, the one on the far end, the output of the net is actually a matrix where you don't do flat layers. You have it reverse back out, and you're sending an image out the bottom. And so you can do a color image where the input coming into that is a black and white image, and the input coming out is a three-dimensional color image. You can also do image repair, where I purposefully damage the image on the input, and the net draws the image on the output. Like, this is ridiculous, and it actually works really well. So I can train a net where the input going into the net is a black and white image. Yeah, grayscale image. So yeah, so this is a real output. So that flower with the butterfly on it, the net decided what those colors should be. So based on the black and white image, it predicted all the colors. You can get this pre-trained. I would start this pre-trained on ImageNet if I was doing this. Yep. And your output is a color image, and I think, judging from people in the room, we don't have Photoshop skills that good to Photoshop that, because that looks believable. You could show someone, hey, this is an image I took last Sunday, but actually it's an image that your grandfather took 3 generations ago, and there's no way it's colored, but you've colorized it using these deep nets. And the image repair is wild too, because that's a super easy training set for you to build. You just purposely damage parts of your image, and the test case is the net needs to learn to redraw the missing parts. So this is the net redrawing the missing portions of the face. And the craziness doesn't stop there. You really, coming out the bottom, you can have whatever you want. If you want the input to be an image and you want the output to be audio, whatever. You need to get a training set where that actually makes sense, but you could do that. And I think one of the ones that I saw recently that I think is super cool, the output is an animation. So the output is not an image, it is an animation, and what the net is predicting is what will happen in the future. So it's training on a video. I've got a still frame of someone walking, and the net is predicting the walking. Like, isn't that wild? Like, think of all the crazy, yeah. So in the future, when the computers are fighting us, they'll be really good at knowing what our next move is based on, like, us bringing our hands up. The other thing that we've done with our data augmentation stuff is at Ziff we've added more augmentation abilities beyond what Keras supports. So we've added in scikit calls, so we can do like histogram equalization. So if an image is dark, you can have it. So I think of these features as popping. So anytime I have an image where I can make it pop more for my eyes, that's going to help the deep net. And so some of us do that by demeaning. If you demean, you'll notice the images kind of pop more, but if you do image histogram equalization, there's other processing functions you can do before you give it the deep net that'll make it pop. And then this example on the right, splicing, you actually take an image like a classroom and you make a pseudo image on the fly where you've just kind of spliced 4 random selections. And what you're allowing the net to do is you might have a use case where the net has never seen a kid with a globe. See the globe on the bottom right? Maybe the net has never seen a kid with a globe because it doesn't exist in the training set as a combination. But by splicing, you're allowing it to generalize a little bit better because it's able to see feature combinations that it may not exist. So this is my final slide, pretty much. So future work, I think I didn't get into optimizers. So a lot of people want to know, well, what's your secret optimizer that you use? A lot of people still use stochastic gradient descent. We've been using this one lately called Nadam. Some people like Atom. Really, the optimizers, they're kind of a hack anyway because a lot of them are assuming this nice gradient descent behavior where in reality, if you really looked at the gradients, it's a nightmare in there. And that's why we do batching to average and different things like that. So I've been really excited about genetic algorithm fine-tuning where you get almost all the way there and then you forget this gradient crap and you just do a gradient-free optimizer. So we kind of played with that, but we haven't done anything worth showing. Fractional max pooling done right. So there's a paper out there from Benjamin Graham in the UK where he's shown that fractional max pooling can be pretty significant because if you go from these max pooling layers from big to small, it's actually too big of a step because I'm reducing it by a factor of 4. I'm going from an image that's 100 down to 25 by 25, and the argument is that is too big of a feature reduction. And so he has a method where he's able to compensate in the middle, and I feel like there's better ways to do it that can improve your net. And then I have a response to this, but so in the future, you're going to have one net to rule them all. Does anyone have any opinions about what that'll look like? What does my brain do? So if you're a human and I meet you on the street, and you're going to throw a bat at my head, or you're going to ask me a question, I have an input. So then the net of the future that I imagine, the input is the same. There's one input, and then the input is like auditory and visual. The net is always looking, it's always listening. And then based on that, it gets routed quickly to secondary subnets that know what to do that information. So if I'm trying to decide, are you going to throw the ball at me or are you going to ask me a question, I need the features first and then I route them. So you'll kind of have this, kind of like the internet is today, you have all these routing, you have this insane network of nets that where they're routing information at a very quick rate where the net can do everything. So you can give it, visually you can talk to your house and ask it a question, or you can yell for help, or you can do something and it'll route.